Little class. Okay, so we're going to talk about rotational dynamics, where previously we mentioned, we talked about rotational kinematics, where we can describe rotation. Like if an object starts at rest and starts spinning with a certain angular acceleration, how fast is it going to be going after a certain time? We need those kinematic equations, but we didn't really talk about what causes that acceleration. And so that's what we're going to do now. So to start out, I'm going to draw some general object. And say it has an axis of rotation, which is perpendicular to the board. And say this object is spinning about this axis with an angular velocity omega. And this is a rigid object, so that means it has a particular shape that doesn't change. Now, in reality, it's possible that the shape of an object could change as you rotate it. Like the Earth, for example, because it's rotating, it bulges out at the equator. So if you spin something really fast in particular, we're going to say just a rigid object, it maintains its shape and it just rotates together. Like the individual parts of this object do not move relative to each other. And what we're going to do is let's look at like one piece of this object. That is a distance r from the axis of rotation. And as this object's rotating, this object is moving in a circle. It has a tangential velocity, and the tangential velocity is equal to r omega. And we want to talk about the kinetic energy of this rotating object. So again, the object is fixed in place, like this axis is not moving. So if you just let it keep rotating, you can leave, come back, it's still going to be in the same place, spinning around. So there's no overall net translation of the object, it is purely rotating. And so we say the tangential velocity of that piece is r omega, and this piece, of course, has kinetic energy. Let's say this is piece 1. And the kinetic energy of this piece would simply be 1/2 m1. Let's just call it v1 squared. We know it's a tangential velocity. And v1 is equal to r1 omega. So if we look at different pieces, they could have a different radius from the axis. So we have to distinguish that this r applies to this mass at a particular distance. But every piece, if we look at two different pieces, let's call this piece 2. In a certain amount of time, this object will complete one cycle, and each piece will have gone through 360 degrees in the same time period. And so they have the same angular velocity. So we can simplify this. We can say 1/2 m1, and then the velocity, we'll have to say r1, but we can just leave it as r1 omega. We do not need omega 1. Every piece on this rotating object has the same angular velocity. Except for the piece right at the center, but the radius is 0 in that case, so it doesn't matter. We can distribute that exponent, and there we go. Okay, so that's the kinetic energy of that one piece. And if we want to know the kinetic energy of this rotating object overall, then we have to add up all the pieces. So we break this object into pieces and add them all up. So the overall kinetic energy, I'll just write the first couple. We have room for 2. Okay, so again, we add up over all these pieces. and I guess 2 is enough, we can see that this 1/2 omega squared, the 1/2 omega squared, that's constant to every term. So we can factor that out. And what I'm going to do is write it like this. We'd have m1 r1 squared plus m2 r2 squared and omega squared. Okay, so if we want to find the kinetic energy of this rotating object, we'd have to calculate this thing here, which fairly difficult thing to calculate in general. But what we're going to do is give this a name. We call this thing in parentheses here the moment of inertia. And with that, we can write the kinetic energy of this rotating object. Actually, I'm going to call it like Kr. Put a box around that. So this moment of inertia, we use a capital I for moment of inertia. And then we have rotational kinetic energy is 1/2 I omega squared. So I make a nice formula. We're kind of hiding the messy part, which is this thing in parentheses. How do we find out what that is? And again, we'd have to do is take our object, we'd have to break it up into pieces and calculate, this term for each piece, add them all up. Now, probably know by now that when you break things up into pieces and add up the pieces, that's a calculus problem. So what are we going to do in this class? Well, the answer is fairly simple. We have a table. It's in the notes. It's also on your equation sheet. So different objects are going to have different, it's called moment of inertia. It depends on the axis of rotation as well as the geometry of the object itself. Like one example, we have a solid sphere about any axis going through its center. Then I is 2/5 mr squared. If you have a spherical shell, that would be a hollow one, then it's I is 2/3 mr squared. So you have a different number. So the moment of inertia depends not just on the mass, but how the mass is distributed. So if you have two spheres that have the same mass, but one's solid all the way through, and the other is just a shell that's hollow inside, the shell is going to have a larger moment of inertia because the mass, or in each of these terms, it depends on the radius squared. The farther away the mass is, the more it contributes to the moment of inertia. And so it'll have a greater moment of inertia if all the mass is in that shell, which is farther away from the axis, than if it's spread uniformly throughout. Now, what actually is a moment of inertia? It's a measure of, the word inertia kind of gives it away. What is inertia? That is a tendency to just keep doing what you're doing. So for linear motion, mass is inertia. If you have a large mass that's at rest, you want to get it moving, it's going to take a lot of force to change that state of motion. And moment of inertia is the tendency for it to, it's just the rotational equivalent of that. If an object is rotating, if it has a high moment of inertia, then it'll be very difficult to stop it from rotating. If it starts out at rest and you want to cause it to rotate, the greater the inertia it has, the harder it's going to be to do that. So this is the rotational equivalent of mass. And so I have a table here. These are things we talked about before, where we have translations and rotations. And it's interesting because we can continue with this table. Let's add mass to it. Or let's add this idea of inertia. For translations, inertia, mass is a measure of inertia, but for rotations, moment of inertia is a measure of inertia. That plays the role for rotations that mass plays for just linear motion. And this table is very interesting, because remember, you can take any equation that we've dealt with for linear motion. Like, let me just take a simple example. We know for translations, we have this equation as long as the acceleration is constant. And if we just look at this table and replace, here we also have this condition that a is constant. If we just replace all these variables, so if we have angular acceleration is constant, so the rotational equivalent of acceleration is angular acceleration. The rotational equivalent of velocity is angular velocity. Initial velocity, that would be initial angular velocity. And then replace a with alpha. And time, leave alone. And again, this is a valid equation. And now we also have like kinetic energy. If we replace we can see like the rotation, the equation we derived for rotational kinetic energy. If you take translational kinetic energy, if you replace mass with moment of inertia and velocity with angular velocity, you get the right form for rotational kinetic energy. And we're saying we can keep expanding this table. Like everything that we talked about for linear motion has a rotational equivalent. It's a pretty amazing thing. But let's look at an example where we can. I have one in the notes. I'll actually pick a different one. We have in the notes I have a rolling wheel, but let's say we have a rolling ball. So looks like a wheel, but let's give it an equator. So let's say this is a solid sphere that's just rolling across the ground. And it's moving with a velocity v. So we want to know the kinetic energy. This object has a mass m and velocity v. It has a radius r. Whether we need that or not, we'll write it down. And let's say, how much kinetic energy does this rolling ball have? Now we need to know that this is a solid sphere. So, kinetic energy. Now it's rolling, so it has translational and rotational kinetic energy. And we're also going to say that it's rolling without slipping. Although so far we don't need that. What I wrote down is true, whether it's rolling with slipping or without. But we can simplify this if we take the condition rolling without slipping into account. But anyways, the translational kinetic energy is just our familiar 1/2 mv squared. And then we have, so that's our translational. Now the rotational, again, this is a solid sphere, so let's look that up. I think it was 2/5, that number in front. Yeah, solid sphere. We have 1/2 I omega squared, and this would be 2/5 mr squared would be the moment of inertia. So here we have 1/2 I omega squared. So remember, translational kinetic energy, 1/2 mv squared for rotational kinetic energy. Replace mass with moment of inertia, velocity with angular velocity, and we just had to look up what I is for a solid sphere. And we can simplify this in two ways. So 1/2 times 2/5, that is 1/5. And then we've got mass here. And then we have r squared omega squared. And this is a part, if we're rolling without slipping, we know that v is equal to r omega. So we have r squared omega squared, that's just v squared. And then we can just combine these two terms. 1/2 plus 1/5, that's 5/10, that's 2 over 10. So we have 7/10 mv squared. So if this ball was just moving with a velocity v, it would have 1/2 mv squared. But if it's rolling, it has more energy because if it was just translating, every particle would just be moving in a straight line. But in addition to that just sideways motion, they're also going through these circles, which gives them additional velocity. And so, yeah, going from here to here, we use rolling without slipping, and I can basically guarantee that I would never give you an example like this where we weren't doing that. So this part, you're safe to just go from here to here. So we can have the kinetic energy of a rolling object. Okay. Let's go back to our... Let me redraw that picture. Time to clean the board again. Or more likely the eraser. But anyways, we've got this general object with an axis of rotation. And let's say we apply a force so this piece is going to rotate. This force is going to cause this object to rotate through this angle delta theta. So we have a force here which we can break into components. Now remember, work is basically a force times a distance. So here we have a radial component of the force and a tangential component of force. Remember, work is basically a force times a distance, but you only want the component of the force in the direction that the object is moving. Well, this object is going through this circular arc here, and so it's always moving in this tangential direction. So the work due to this piece here would be equal to the work due to this force would be the tangential component of the force times the angle that it rotated through. And we can use not yet. So let's say this force is applied at a distance r. Sorry, let's say that this arc length is delta s. Sorry, got ahead of myself there. So force times distance, that would be the arc length. And then we can say the arc length would be r times delta theta, using our familiar S equals r theta equation. Okay, so now we can look at this part here. That's equal to torque. So the work done by this force is equal to the torque times the angular displacement. which, if you look at work, that'd be force times delta x. Again, the rotational equivalent of a force is a torque. So, and here for translations, we have forces. For rotations, we have torque. So again, that's like another one of these substitutions we can make. Work is force times displacement. We can replace force with torque and displacement by angular displacement. Okay. Now, remember the work energy theorem, where the work is equal to the change in kinetic energy. So we can say that the torque times this angle is equal to the change in kinetic energy. Let me get rid of this. So remember kinetic energy, 1/2 I omega squared. We're talking about a rigid object. So the moment of inertia is not changing. If the object was deformed, then the moment of inertia would change. We're just talking about a rigid object. So we have, just from the work energy theorem, the work is torque times delta theta. And this would be the final kinetic energy. That's the initial kinetic energy. And we can factor the 1/2 I out of this. Okay, now we're going to have to assume right now that we're applying a constant force at a definite location. So we have a constant torque acting on this object. Now the result does not depend on this assumption, but I want to use our rotational kinematics that we talked about just recently in chapter 8. Where we can say omega squared equals omega naught squared plus 2 alpha delta theta. Or in this case, this is like, we can say final and initial values here. And so if we, again, this depends on a constant angular acceleration, but let's just assume that's the case. The result is more general than that though. So if we subtract omega initial from both sides, we have omega final squared minus omega initial squared is 2 alpha delta theta. So let's put the result down here. Okay, so we have 1/2 I times 2 alpha delta theta. Now the 1/2 and the 2 cancel each other out. And we have a delta theta on both sides, so we can cancel those out. And we get the result, torque equals I alpha. Now, we showed that for this like one force acting on this rigid object. If we had multiple forces, we could repeat this for each force. The net result is, the net torque equals I alpha. Compare that to Newton's second law. Net force is equal to mass times acceleration. If we replace force with torque, mass with moment of inertia, and acceleration with angular acceleration, again, we get a valid equation. So this table is a pretty amazing thing. Everything we talk about with translations applies to rotations as well. You can take any of our translational equations and get a rotational equivalent. And this is basically Newton's second law for rotations. So what we've talked about so far was statics. So in static equilibrium, net torque is 0. If the net torque is 0, that means that the angular acceleration is equal to 0 and we have no rotation, or no change in rotation. It could be rotating with a constant angular velocity. It's not going to speed up or slow down. So, yeah, what we talked about with statics is valid. But now we can see if we have a net torque, we can say more than that's going to cause a rotation. Now we know the angular acceleration. And it's kind of nice writing it this way. I mentioned before that moment of inertia is kind of like the rotational equivalent of mass. We can see that that's the case here. If we have let's say we apply a fixed torque on an object. If that object has a large moment of inertia, we're dividing by the moment of inertia, and so we're going to have a small angular acceleration. If we have a small moment of inertia, large acceleration. And so, yeah, this moment of inertia is, well defined. The term is well defined. It's a measure of rotational inertia. Higher this is, the harder it is to change its state of motion. Should point out that we can write I as a formula. We break it up into pieces. And just add up all the pieces. And we can see that the units are going to be kilogram, the basic SI units anyways, kilogram meters squared. So those are units per moment of inertia. And again, it's something that we typically look up. There's one example, though, where we can find the moment of inertia precisely. And that is if we have a point particle. So let's say we have a mass on a string. And again, the string is so light. Technically we could find the moment of inertia of the string. But let's say a string is so light we can ignore it. Then the moment of inertia of this object would just be mr squared. So if you have a point particle, you can find its moment of inertia. Otherwise, it'll be some extended object, in which case you just look it up. You can always calculate them, but that requires calculus, so we just look them up. Now, I should go back and say one more thing about moment of inertia. The axis of rotation plays a big part. If you go back to our table, you can see from the picture, they show the axis of rotation. Like, say that one right in the middle. Let me describe that. A thin rod about axis through center, perpendicular to length. And, or if you look at this example, you have a rod going, parallel to its length. You definitely get different results. And actually another thin rod example we could do. Let's look at that example. So we have a thin rod. Let's say we rotate it about an axis like this. So it'd be like doing this. So it's rotating about the middle. And if we look that up, the moment of inertia that'd be 1/12 the mass times the length squared. But what if we had a different axis of rotation? What if we rotated it about an end? You could certainly do that, just grab it at the end and have it spin around like this. Well, you see that's not in the table. Or maybe not even the end, how about just some arbitrary point? So you just rotate it like this, about some axis anyway. Now notice that this is the center of mass of the object. So we can say the moment of inertia through this axis through the center That's ICM, for center rotation about the center of mass. And there's something called the parallel axis theorem, which we can prove, but it's in the notes, so I'm not going to bother going through it because it'd be, you know, fair effort involved. And most of you probably don't want to see it, but if you do, then you can read it in the notes. But the name is important. Parallel axis theorem, that's the case we have here. Where if we look at an axis that's parallel to the one going through the center, like we know this one here. So if we know the moment of inertia through the center of mass, we can find the moment of inertia at some distance away. We call that distance h, as long as that other axis is parallel to the one that we already know. So it's called the parallel axis theorem, and the formula is very simple formula, actually. We take whatever we have from the rotating about the center of mass, and we add mh squared, where h is the distance to the new axis of rotation. And yeah, that's it. That's all there is to this. It's actually a fairly simple equation. And, you know, of course, m would be the mass of the entire object. An important consequence of this is we can see the axis that gives you the lowest moment of inertia is the one going through the center of mass. Because if you're going through the center of mass, h is 0, this whole thing is 0. So if you go about a different different axis that's not through the center of mass, h is going to be, it's just the distance. You don't care if it's to the right or left. Well, one thing, because it's rotating, so it wouldn't even make a difference, but it's squared. So this is always going to be positive. Unless it's 0, but then you're at the center of mass anyways. So in general, the moment of inertia is a moment of inertia through the center of mass plus something extra. And so if you're, like the highest moment of inertia you could get is rotated about one end. And then you would just add, in that case, the moment of inertia through the end of the rod. That'd be 1/12 ml squared. Plus we have m. And then h would be L over 2 in that case. So we'd have 1/12 ml squared. And then this would be 1/4 ml squared. Or 3 over 12. So if you add it up, we get 4 over 12, which is 1/3. So a significantly higher moment of inertia if you're rotating it about the end. Okay. And this can be a very useful formula. It's called the parallel axis theorem. There's also one called the perpendicular axis theorem, but we're not going to bother with that. And yeah, I think we'll stop here. There's actually one more topic we need to consider. And if you look in our table, there's one thing that's missing here. Something we talked about for translations that we have not mentioned with rotations. And I always ask students in a live class, and usually after several minutes, someone points out, what about momentum? So momentum, we have P, mass times velocity. So what we're going to do, this will be a separate lecture, we're going to define angular momentum, where we use the letter L. And we're going to define angular momentum by replacing mass with moment of inertia and replacing velocity with angular velocity. So I'm pointing out in lab, we have two labs. One is conservation of P, the other is conservation of L. We just did this lab, so yeah, that conservation of L, that's angular momentum. That's what we will talk about next. But this will be it for now.